Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry made easy. In this lesson we're going to cover these specification points looking at enthalpy and the definitions around this topic area. So enthalpy will be a new term for most people at A-Level, and basically it is a measure of thermal heat energy. And when we're dealing with enthalpy, we're usually dealing with enthalpy changes. So we're looking at changes in the heat energy in a system. And what we mean by the system is the reactants and the products if they've been formed within a particular reaction vessel. So here we have a closed system in the form of a test tube with a thermometer in it in order to measure these temperature changes. And we define everything within the test tube, within our closed system, as the system. And when we're talking about everything, we're talking about the matter within it. And then everything outside of the system, we then just call the surroundings. And as mentioned before, what's going to happen is we're going to allow some sort of chemical transformation to occur. We're going to take an initial temperature, we're going to take a final temperature, and then that gives us our overall change, and then we call this the enthalpy change. Now, any change in physical sciences is going to be shown using the delta symbol. And all of this leads to delta H. And delta H, or the change in enthalpy, has the units of kilojoules per mole. And at A-level, we show this as kilojoules mole to the -1 reciprocal. And in order to show these enthalpy changes, we can show them in the form of an enthalpy profile diagram. And we're going to look at two, one for an exothermic reaction, one for an endothermic reaction, and explain what those terms mean in a minute. What you'll notice is the y-axis has the actual energy, or the enthalpy, and the units kilojoules per mole. Whereas the x-axis is something labelled as reaction progress. You might also see it as reaction coordinate. And that is just basically time. So it's from the start of the reaction, all being reactants going to products, and the energy changes are being plotted as a result of that change. For both enthalpy profile diagrams on the left and the right, I'm going to plot the reactants at the same enthalpy value, so that they're relatively exactly the same. And I've used the label R just to show reactants. In an endothermic reaction, the products have a higher enthalpy than the corresponding reactants. And we're going to show this in the left-hand side enthalpy profile diagram. Now remember, enthalpy is all about enthalpy change, so we can show this diagrammatically by showing a delta plus and it's positive. To show how the reactant and the product energy levels link together, we're going to show the energy journey between the two. Now, you might imagine that you just draw a line going from reactant to product, but there is an activation energy for any reaction. So what actually happens is the reactants have to gain enough energy to break all the bonds within the reactants, and then on the downward slope here, we have the new bonds being formed. The activation energy is the minimum amount of energy needed to begin breaking these reactant bonds, and this is shown from the top of the peak of this curve to the reactant level. And if you're watching these videos in order, later on when we look at collision theory, we'll explain what dictates what this activation energy is and how that relates to the reactants and the kinetic energy that they possess. On the other hand, an exothermic reaction, the products are lower in energy than the reactants. And again, we can show this delta H, this change in enthalpy, on these energy profile diagrams by extending the reactant line to where the products is and then showing in a diagram it going downwards. Now, one thing worth noting that these are like vectors, so if it's going down, it's going to be a minus, whereas an arrow going upwards is going to be a positive value. And it's all in relation to your values on the y-axis. So if you were going from one point here upwards, then obviously you're a positive change. And if you were going from this reactant downwards, then you're obviously making a negative change. And exothermic reactions, they too have activation energies. So we're going to extend up our curve until it meets the products. And then your activation energy is going from the reactant levels again to the top of the peak, and we label that EA. So one thing to note is enthalpy is really a measure of the energy contained within the chemical bonds. So in an endothermic reaction, comparing the reactants to the products, there is more energy within the substance in the product form than there was in the reactant form. So this energy is locked in the chemical bonds that are there. Now, because energy cannot be created or destroyed, in an endothermic reaction, if the chemical energy has been increased, then that energy has got to come from somewhere. And it's come from the thermal energy in the surroundings. So that thermal energy has been converted into chemical energy. And so the thermal energy of the surroundings has decreased. And this is why endothermic reactions result in a decrease in the temperature of the surroundings. Now, vice versa, in an exothermic reaction, the change between the reactants and the products is a minus delta H. So that means that the chemical energy has decreased. However, again, because energy can't be created or destroyed, if we've decreased the chemical energy, it has to have converted into something else. And so what has actually happened is it's increased the thermal energy in the surroundings outside of it. Hence why we find that exothermic reactions heat up the surroundings, and we see a temperature rise in our thermometer. Now, in chemistry, most things can be seen as some sort of reactant changing to some sort of product. And the arrow is used to designate this transformation. And so every chemical transformation will have an enthalpy change. Now, because you can't directly measure the enthalpy of a reactant or the enthalpy of a product, you always look at this delta H. And so that scientists and chemists in particular can compare these universally across different laboratories, across different places on Earth, they use standard conditions and they ensure that the reactants and the products, and whichever chemical species they're looking at, are in their standard states. Now, the standard conditions are room temperature and pressure. But obviously that is subjective depending on where you are. And so that has been set in stone as being 100 kilopascals, which is about 1 atmosphere, and then 25 degrees Celsius or 298 Kelvin. And standard states just means whatever the chemical species is it solid, liquid or gas at this room temperature and pressure, this 100 kilopascals and 298 Kelvin. And if both standard conditions and standard states are met, then we can designate the measurements and the enthalpy change with this symbol here. So if you ever see this, you know it's been measured under standard conditions and standard states. There's a series of 4 definitions that you have to be able to be well versed in just repeating in the exam to pick up easy marks. The first one to start with is the standard enthalpy change of a reaction, because we can think of all transformations in chemistry as going from reactants to products, where reactants is what you start with, products is what you end up with. Now, this is the enthalpy change when molar quantities of reactants are reacted together. So take, for example, iron reacting with chlorine to form iron trichloride. The standard states are shown here. Iron would be a solid metal at room temperature and pressure of the 100 kilopascals and 298 Kelvin. Chlorine would be a gas, and the iron trichloride would be a solid. Now, the molar quantities are to do with the ratios needed to make the product. So iron here, we need 1 of those, and we need 3 chlorines. Iron, it exists in itself, so that's absolutely fine, but chlorine is diatomic. So we are going to need 1.5 chlorine molecules in order to form our iron trichloride. And so the molar quantities are actually now correct and are shown in the equation. So we can see this first one as kind of the generic idea of all enthalpy changes. If we look at the specific example of standard enthalpy change of combustion, then what we notice is it's the enthalpy change when 1 mole of a substance is burned completely in oxygen under standard conditions with all substances in their standard states. You'll see a similarity throughout all of these, that we have standard states and standard conditions. Simplest example could be methane burning in oxygen. At this point, they're both gases under standard states. When it references burning completely in oxygen, we mean complete combustion. So methane is going to produce carbon dioxide and water. And a standard enthalpy change of combustion will be given the symbol delta CH. Now, another enthalpy change is the standard enthalpy change of formation. And this is when 1 mole of a compound is formed from its elements under standard conditions. Now, it's important just to reiterate that a compound is when there's more than one type of element in a substance. And the other thing worth noting is that elements sometimes could be monoatomic. For example, sodium, Na, is on its own, or they can be diatomic or polyatomic. For example, diatomic are the halogens, chlorine is Cl2. You've got polyatomics such as sulfur, which is S8, or phosphorus, which is P4. And so an example could be sodium and chlorine as the elemental forms coming together to form the compound sodium chloride. And so their state symbols will be those at standard states under the 100 kilopascals and 298 Kelvin. And standard enthalpy change of formation is given the symbol delta FH. The final standard enthalpy change definition that we need to know is that of neutralization. And this is when you have an enthalpy change of when 1 mole of hydrogen ions reacts with 1 moles of hydroxide ions to form 1 mole of water under standard conditions and standard states. So here we have the 1 mole of hydrogen plus ions, 1 mole of the hydroxide ions, and then this forms our 1 mole of water. And obviously the states are as followed. And if you were to take 1 mole of a strong acid and 1 mole of a strong alkali to form 1 mole of water, then the standard enthalpy change of neutralization works out to be minus 57.9 kilojoules per mole. Now, something that you might see a pattern, especially with combustion, enthalpy change, formation, and neutralization, is that they all have the similarity of 1 mole of something either being combusted or formed. And you'll also notice that the units for all of these different types of enthalpy changes are kilojoules per mole. Now, an exam question that allows us to apply some of the ideas that we've looked at in this video is this question here. I'd like you to pause the video here and have a go at just this 2-mark question using the data that's given. Okay, so now we're going to go look at the answer and just check that you've got the right ideas and you've applied the information in the correct way. Okay, so the actual question is looking for the enthalpy change of formation of N2O to be shown in an enthalpy profile diagram, which is what we need to put in the actual answer box here. Now, you've been given some information for the formation data shown by the delta FH here in this table. You've been given N2O and you've been given NO. Now, we don't need NO, and we'll think about this in a moment. We do need the N2O because this is our delta FH, which is our formation data. And so that's going to be our product. That's what we're forming. We've always got to think of reactions as reactants going to products. In this case, our products are going to be the compound N2O. So enthalpy change of formation, if you remember from previous slide that we were looking at the idea of this is the 1 mole of a compound formed from its elements. So N2O, the elements that make up N2O is nitrogen and oxygen. Now these are both diatomic elements. So the N2 and the O2 and the elements are reactants. In terms of the ratio of elements, N2 and N2 here, that's absolutely fine because we've got two nitrogens on the left-hand side of the arrow and two nitrogens on the right-hand side of the arrow. But our oxygen, we only need one oxygen, even though the elemental form is 2. So we're just going to put a half in front of the O2 to show that our molar ratio is half compared to the N2 element. And so basically we've constructed the equation for the formation of N2O. And what you should know is nitrogen and oxygen are gases at standard temperature and pressure, and N2O, it would be unsurprising to know that this is also a gas. Now we know from our delta FH data that it's plus 82, so we know that going from the reactants to the products that it is an endothermic process. And we know we show this on these energy diagrams by showing an increase in the y-axis, so an upward arrow. Next is we just need to take all these ideas and concepts and plot them on the enthalpy profile diagram here. So we're going to have our reactants on this side, we're going to have our products on this side, and because of the plus 82, we're going to show an reactants here and products here and an increase going between the two. So here we have the reactants and the products. I'm now just going to arbitrarily show that we've got a plus 82 kilojoules per mole. And whilst it does say that you are not expected to show the activation energy for the reaction, I don't think it's too difficult to show that we're going to have a upward trend like so, going to the N2O. And then our activation energy, if this was the case, would be the highest point on this peak here and would look like so. So if you got this, you're looking at the 2 marks, mainly first mark for in knowing that your step levels of your diagram are increasing, going from reactants to products because of the plus 82 and the label that's there. And then the second mark is for the correct reactants and products and their state symbols in the correct locations on your enthalpy profile diagram. So in this video, we've looked at all of these different specification points, looked at all the different definitions that you need to know around enthalpy, and also looked at constructing enthalpy profile diagrams to show enthalpy differences in reactants compared with products. Hopefully you found this video useful. If you have, please ensure you like it and subscribe to the channel for more videos on A-level chemistry essentials.